In this chapter, we're going to be going over partial fractions, and we're going to start with the decomposition of rational expressions. So suppose we have this following equation here, and we have 2 over x plus 1 plus 3 over x. So we are adding two rational expressions, and then we get this result on the right, 5x plus 3 over x times x plus 1. So the way that we would have to arrive at that answer is by getting a least common denominator. But let's say we're going to start with the right this time, and we want to go back to the left side of the equal sign. So we want to split up the rational expression into two or more other rational expressions. What this is called is a partial fraction decomposition, and each term in the sum is called the partial fraction. So 2 over x plus 1 would be one of the partial fractions, and 3 over x would be the other partial fraction. So for example, let's determine whether the partial fraction decomposition of 2x over x squared minus 1 is 1 over x minus 1 plus 1 over x plus 1. So to show this, we need to add those fractions together. So we need to do 1 over x minus 1 plus 1 over x plus 1, and we need to show that it equals 2x over x squared minus 1. So in order to add fractions, we need to get common denominators, and in this case, the least common denominator is going to be x minus 1 times x plus 1, which essentially just means in this case, we need to multiply each fraction by the other fraction's denominator. So we multiply the first one by x plus 1 over x plus 1. We multiply the second one by x minus 1 over x minus 1. And we will end up getting 1 times x plus 1 for the first numerator over that common denominator, x plus 1 times x minus 1, plus x minus 1 in the second numerator over that common denominator. And we can go ahead now and combine these fractions into one fraction because they have a common denominator. So that's going to be x plus 1 plus x minus 1 over x plus 1 times x minus 1. And the 1's are going to cancel in the numerator. And then we can combine the x's, which is 2x for the numerator. In that denominator, that's multiplying conjugates. So you could FOIL out that denominator, x plus 1 times x minus 1, or you can know that since they're conjugates, it's going to be the first one squared minus the second one squared, which is x squared minus 1. Okay, so we can see that that's exactly what was in the question. So in this case, the partial fraction decomposition of 2x over x squared minus 1 is 1 over x minus 1 plus 1 over x plus 1. Okay, so now we're going to actually see how we can figure out these partial fractions without being given them. So to form a partial fraction decomposition from a rational expression, we need to follow these steps here. So they're going to seem pretty confusing until we see an example. But if we have a rational expression, f of x over g of x, step 1 is going to be if f of x over g of x is not a proper fraction. So that means if we have something like this example here, where the degree in the numerator is greater than the degree in the denominator, before we do anything, we first have to divide them, and then we're going to end up having to work with the remainder over the divisor over here on the right. Okay, so for step 2, this is where most of them will be starting off. Our first step is to essentially factor the denominator, and we have to factor it completely. And what we're going to have is we are going to have linear factors and or quadratic factors. So the ax plus b to the mth power is linear, and the cx squared plus dx plus e to the nth power is a quadratic factor. And the way that we're going to do it is we are going to say that for each distinct linear factor, we're going to place a kind of a placeholder, which is going to be a constant, capital A, over that linear factor ax plus b. And if we have a repeated linear factor, meaning we have an exponent, so ax plus b to the mth power, that means we need to have m number of linear factors. So we need to have one without the exponent, with an exponent of 2, and then we need to keep on going until we get to the mth exponent. Okay, so that's for linear factors. For quadratic factors, what we're going to have is for each distinct quadratic factor, the decomposition has to have the term bx plus c over that quadratic factor. So notice the difference between the linear one. The linear one has a constant in the numerator. The quadratic has a linear factor in the numerator. And then, just like before, we can have repeated quadratic factors like we did for the linear factors. And for this one, it's going to be pretty similar to what we were just saying. We're going to have, if we have a quadratic factor raised up to the nth power, then we need to have all of the quadratics from the first power to the second power, all the way to the power of n that we have. And we need these linear factors, those linear expressions in each numerator. And what we're going to have to do here is our goal is to solve for these constants a, b, and c. And once we have those, then we're going to have our partial fractions. And here are a couple of useful techniques for actually doing this. Once again, this will make sense once we do an example. So for the decomposition into partial fractions, method 1 is going to be for linear factors. Once we have the setup that we just did in these steps above, we're going to multiply each side of the resulting rational equation by the common denominator, and then we're going to have to solve for a or b or c by plugging in values into x. And the way that we can do this for linear ones is by plugging in the 0 of each factor into the equation. And I'm not going to bother reading off the other things. We'll see why that's useful in a second. Method 2 for quadratic factors. Once again, we're going to multiply each side of the resulting rational equation by the common denominator, get all the terms on the right side of the equation, and equate the coefficients of the like terms to get a system of equations. Okay, so let's just jump into examples so we can see how this makes sense here. Find the partial fraction decomposition of negative x over x plus 1 times x plus 2. So first, let's recognize that the degree of the numerator is less than the degree of the denominator. If we FOILed out the denominator, we would have x squared. So we don't need to do any division here from that step 1 that we mentioned. So let's start by just rewriting the expression negative x over x plus 1 times x plus 2. So the next step would be to factor the denominator. The denominator is obviously completely factored. So what we have to do next is set this equal to a sum of the partial fractions using those factored denominators. These are linear factors, x plus 1 and x plus 2, and neither of them have any exponents. So what we're going to do is say the first fraction can have a denominator of x plus 1. The second one will have the denominator of x plus 2, and that's all we have to worry about. And since these are linear, then the numerators are going to be a constant. We can call them a1 and a2. I'm just going to call them a and b. Okay, so now for the next step, what we have to do is multiply both sides of the equation by this denominator over here, the original denominator, which is the least common denominator. So we're going to multiply both sides of the equation by x plus 1 over, or x plus 1 times x plus 2. What that's going to do is that's going to cancel every single denominator. So the denominators, the original denominator is just going to completely cancel, and we're going to be left with negative x. For the next one, the x plus 1 is going to cancel. We're going to be left with a times x plus 2. And then for the one all the way on the right, the x plus 2 is going to cancel. We're going to be left with b times x plus 1. Okay, so our goal here is to solve for a and b. But we only have one equation. We have one equation with a and b in it. But what we're going to do is use the fact that we can plug in any value for x and then solve it for a and then solve it for b. So we're going to plug in the value of x. That's going to cancel off this term. And we're going to plug in the value of x after that. That cancels off this term, and that'll allow us to solve for a and b. So let's solve this for a first. So we solve this for a by canceling this b term over here. The way we cancel this is it is the 0 of x plus 1, meaning it's the value for x that we plug in that makes that whole term equal 0, which is obviously just negative 1. So let's go ahead and do that. So it's going to be negative 1, so that's the left-hand side over there, negative x, equals a times negative 1 plus 2 plus b times negative 1 plus 1. So then what happens here is we end up getting positive 1 on the left equals a times 1 plus b times 0. So that's what we wanted. We wanted that b term to cancel off. And now we just end up getting a equals 1. Okay, so let's do a similar thing for b. Let's solve for b. So solving this for b, we need to plug in the value of x. That's going to cancel off the a term. So we need this term to cancel off. And that means we need to let x equal negative 2. Because x plus 2 equals 0 will give us x equals negative 2. So we're going to plug that into all of the x's. So that's negative 2 for the one on the left equals a times negative 2 plus 2 plus b times negative 2 plus 1. And solving this for b now, we get 2 equals a times 0, which is what we wanted because that term is going to cancel, plus b times negative 1. So we get 2 equals negative b, essentially, which gives us b equals negative 2. So we just pretty much did all of the hard work. Now we just have to use what we created up here and pretty much rewrite this, except without using a and b. We're going to plug in what we just found for them. So originally we said we were looking for the decomposition of negative x over x plus 1 times x plus 2. We said that was a over x plus 1, but the a value we found was 1. So 1 over x plus 1 plus b over x plus 2. B is negative 2. So that's b over x plus 2. So that is the decomposition of that rational expression. So let's do one that's a little bit harder now. So we want the partial fraction decomposition of 2x to the fourth minus 8x squared plus 5x minus 2 over x cubed minus 4x. So first we have to recognize that the degree of the numerator is greater than the degree of the denominator. So what we actually have to do here is divide this first. So dividing this, we have to do this with long division. That's 2x to the fourth minus 8x squared plus 5x minus 2 over x cubed minus 4x. Okay, so we need to think, what do we have to multiply x cubed by to get to 2x to the fourth? Or we can divide those leading terms on the side. Either way, we're going to end up getting 2x. I'm going to put that right here. Now we have to multiply 2x by that divisor. 2x times x cubed minus 4x. We get 2x cubed minus 8x squared. And actually, when we subtract this, those both end up canceling. And we have to bring down what we didn't use. And that's actually it. So that one's actually pretty easy. We knew to stop there because the degree of 5x minus 2 is less than the degree of the divisor, x cubed minus 4x. So let's reset this back up here. We have the original expression, and using that division algorithm, we know this equals 2x, the quotient, plus the remainder over the divisor. So we have to think back to setting this up using the division algorithm. And what we have to do now is we need to work with this remainder portion over here. Okay, so let's go ahead and set this up. So we are going to use 5x minus 2 over x cubed minus 4x. So just to not have it be super clumped, let's factor this. So we always need to factor the denominator. There's a GCF of x. If we factor out an x, we're left with x squared minus 4. And we can actually factor that using difference of squares. That factors to x plus 2 times x minus 2. Okay, so what we have here is 3 distinct linear factors. We have x, x plus 2, x minus 2. So we do exactly the same thing what we just did. We're going to give them each their own fraction with some constant in the numerator that we have to solve for. So it's going to be a over x plus b over x plus 2 plus c over x minus 2. And we need to multiply both sides of this equation by the least common denominator, which is just the original denominator, x times x plus 2 times x minus 2. And then we're going to end up getting 5x minus 2 on the left because the denominator canceled. And then for the a term over here, the x is going to cancel. We're going to be left with a times x plus 2 times x minus 2. And then for the next one over here on the right of that, the b term, everything, or the x plus 2 is going to cancel. We're going to be left with b times x minus 2. And then lastly, for the one on the right, the x minus 2 is going to cancel. So we're going to be left with c times x plus 2. Okay, so kind of messy here, but now we just do the same exact thing that we did before. Let's start by solving for a. So what we have to plug in for x in order to find a is the 0 from a's denominator, which is x equals 0. So if we let x equal 0 here, that's going to end up being 5 times 0 minus 2 on the left equals a times 0 plus 2 times 0 minus 2 plus, now if we plug in a 0 into these other ones, they're going to completely cancel because they have an x in them, whereas the a term did not. So these two terms completely cancel, and we're going to be left with negative 2 on the left equals, on the right, we have 2 times negative 2, so negative 4a. Solving this for a is going to give us a equals positive 1/2. Divide both sides by negative 4. Okay, next let's solve this for b. And if we're going to solve this for b, we need to plug in the value of x that makes b's denominator 0, which is going to be x equals negative 2. So we have to let x equal negative 2 into the original right up here. So it's going to be 5 times negative 2 minus 2 equals a times negative 2 plus 2. That is the factor that's going to make that cancel off. And then for b, it's b times negative 2 times negative 2 minus 2 plus c times negative 2 times negative 2 plus 2. So once again, the a and the c are going to completely cancel off here, which is what we wanted. And on the left-hand side, we get negative 10 minus 2, so negative 12. And on the right-hand side, we'll just end up with the b term. The b term ends up being negative 2 times negative 4, so positive 8b. Divide both sides by 8, and we end up getting b equals negative 12 over 8, which simplifies to negative 3 over 2. And the last one here, we need to solve for c. So the factor that makes the denominator for c 0 is going to be x equals positive 2. So we're going to plug in x equals 2, and we're going to solve this for c. So it's 5 times 2 minus 2 equals a times, so what you could do here, I'm just going to plug these in while I talk. What you can do here is, you know, the b and the a term are going to cancel, so you don't even need to write them. I'm just going to write them just to show my work. And all you need to do is write c times 2 plus the 2. So maybe going forward I'll do that. So on the left we get 10 minus 2, so 8. 8 equals, the a and the b cancel because they both have a 2 minus 2, so 0 in them. For c, we end up getting 8c. Solve that for c, we get c equals 1. Okay, so we have our a value, we have our b value, and we have our c value. So all we have to do is take those and plug them in to here. And then to finish it off, let's plug it into this whole entire thing. Okay, so I'm just going to rewrite this first one. And then instead of writing 5x minus 2 over x cubed minus 4x, that was what we just found. So I'm going to replace it with what we just found. Okay, so it was the original question that we had, that 2x to the 4th expression, and we said that that equals, after we divided it, it equals 2x plus the remainder over the divisor. But instead of using that version of it, let's use the version right here by plugging in a, b, and c. So plugging in a, plugging in b, and plugging in c into that, we end up getting 1/2 over x, which simplifies to 1 over 2x, plus negative 3/2 over x plus 2, which simplifies to negative 3 over 2 times x plus 2, plus 1 over x minus 2. Okay, so that one was definitely a little bit more complicated. And let's do a couple more here. So the next one's going to be with repeated linear factors. And what that means is we're going to have a exponent on the linear factor in the denominator. So let's start off by writing the original, 2x over x minus 1 cubed. So obviously we don't need to divide here because the degree of the numerator is less than the degree of the denominator. We don't need to factor any denominators because it's already completely factored, x minus 1 cubed. So now we just need to figure out how we're going to write these partial fractions on the right. The part in the instructions that we went over the steps that's a little bit confusing. Anytime you have an exponent on that factor, you need to have that many partial fractions. And since these are all linear, they're all just going to have constants in the numerator, so a, b, and c. So the first one is going to be a divided by, so the three partial fractions we're going to have, the first factor is going to have an exponent of 1, so that's just x minus 1. The second one is b over, the second one has an exponent of 2, x minus 1 squared. And the last one has an exponent of 3, x minus 1 cubed. So if you have a repeated factor, you start with the exponent of 1, and you keep on increasing it until you get to that exponent. Okay, so once we have that, actually, it's not too difficult. We have to just multiply everything by the least common denominator, which as usual is just the original denominator. So multiply everything by x minus 1 cubed, and then let's go ahead and see what we have left over. So when you multiply it by the first one, the x minus 1 cubed is going to completely cancel off, and we're just going to be left with 2x on the left. When we multiply it by the a term, we're going to have one of those factors of x minus 1 cancel, and that means we're going to have two of them left, so it's going to be x minus 1 squared. When we multiply the b term, we're going to have two of the factors x minus 1 squared cancel, so we're going to be left with one of them. And then lastly, when we multiply the c term by it, we have x minus 1 cubed divided by x minus 1 cubed. They completely cancel, and we're just left with c. So now we need to find a, b, and c. And it's going to be the easiest to solve for c first. And that is because if we let x equal 1, positive 1, then we'll notice that the a and b terms both completely cancel because 1 minus 1 is 0. Okay, so let's plug in a 1. So it's going to be 2 times 1 on the left equals a times 1 minus 1 squared plus b times 1 minus 1 plus c. Pretty simple. All we have to do here is see that it's going to be 2 equals c because the a and b terms cancel, so c equals 2. So now we need to solve it for a and b. There is an issue this time though, because all of these denominators have the same 0 value. They have the same root, and that is positive 1. We just used positive 1, and we found c. We're not going to be able to use it again to find a and b, but what we can do is plug in any value for x and use that to help us find a and b. So what we need to do is plug in two separate values of x, and that'll give us two equations with a and b. So two equations, two variables, we can solve them for a and b. So let's start by plugging in 0. So let's plug in let x equals 0. The reason why I'm picking 0 here is because 0 is a nice, easy number to plug in. You can plug in any number you want. So on the left-hand side, it's going to be 2 times 0 equals a times 0 minus 1 squared plus b times 0 minus 1. And then let's plug in for c. We know that c is 2, so let's substitute it. So let's simplify this a little bit. We get 0 equals a times negative 1 squared, which is just 1. And then it's going to be b times negative 1, so minus b plus 2. And now we need to do this same concept here. We need to solve for a and b again, so same exact thing. I'm just going to label it so it looks kind of clean. We get to pick whatever value we want for x. Let's use -1 because that's also a good number. So we plug in -1 into all the way up here again, and we end up getting 2 times -1 equals a times -1 minus 1 squared plus b times -1 minus 1 plus c. So once again, we plug in 2 into c, and we end up getting -2 equals a times -2 squared, which ends up giving us 4a. And then for b, we end up getting b times -2, so minus 2b, and then plus 2. And we can simplify this. Let's subtract 2, the c value for 2 to the left. We get -4 equals 4a minus 2b. And maybe one more time here, let's go ahead and divide everything by 2, just to make this as simplified as possible. Divide both sides by 2, we get -2 equals 2a minus b. So now we have essentially two linear equations with two variables. So we can solve this using the substitution method, we can solve it using the addition method, we can solve it using matrices. So I'll leave that for you guys to test just because it's something that we've done. Either way, we should end up getting a equals 0 and b equals 2. So you just treat the a like an x, the b like a y, and solve those linear equations. Okay, so now we have everything. We have c, we have a, and we have b. So let's go ahead and plug them in to how we started it. So we're going to essentially just plug them in right here, and that's going to be our answer. So let's rewrite that. So we end up getting the decomposition for 2x over x minus 1 cubed is 2 over x minus 1 squared plus 2 over x minus 1 cubed. And notice that I didn't even write in 0 over x minus 1 for the a term, because it obviously just would have been 0. Okay, let's do 2 more of these ones. So for this one, we want to find the partial fraction decomposition of x squared plus 3x minus 1 over x plus 1 times x squared plus 2. So we have a distinct linear factor in x plus 1, and then we also have a distinct quadratic factor in x squared plus 2. Okay, so let's go ahead and set this up. So we don't need to worry about dividing because the degree of the numerator is less than the degree of the denominator. And we also don't need to worry about factoring the denominator because it's already factored. So we can't factor that quadratic anymore because it is irreducible or prime. Okay, so we have two factors down here. We don't have any exponents, so that means we're just going to have two partial fractions. We're going to have one for each of them. X plus 1 in the first denominator, x squared plus 2 in the second denominator. So since the first x plus 1 denominator is linear, it's going to have a constant in the numerator that we have to solve for, just like we've been doing. However, since the second one is quadratic, this numerator has to be linear. So it's going to be b times x plus c. So it's going to be like that every time for a quadratic. It's essentially 1 degree less. So 1 degree less than a linear expression is constant. 1 degree less than a quadratic expression is linear. Okay, so now we need to solve this, just a little bit more complicated. But we're going to start the same way. We're going to multiply everything by that denominator, that least common denominator, the original denominator, which is x plus 1 times x squared plus 2. And then we're going to rewrite it and see what cancels off. So on the left-hand side, the whole denominator cancels, and we're just left with x squared plus 3x minus 1. on the right-hand side for a, the x plus 1 cancels, and we're left with a times x squared plus 2. And then for the b term, well, the bx plus c term, I should say, the x squared plus 2 cancels, and we are left with bx plus c times the x plus 1 factor. Okay, so we can definitely see that it's a little bit more complicated here, but we're going to start the same way. So let's look for a, and we have to use the 0 from a's denominator, which is x plus 1 equals 0. So we're going to use x equals -1. So let's go ahead and plug that in and see what happens here. So it's going to be -1 squared plus 3 times -1 minus 1 equals a times -1 squared plus 2 plus, so you could recognize that this whole term is going to cancel over here because it's going to be -1 plus 1, but let's just write it out for practice. So -1 plus 1. So yep, that whole right term is going to cancel, so we do not even have to worry about it. So simplifying the left-hand side, we get 1 minus 3 minus 1, which ends up giving us -3. And then for the a term, we get -1 squared is 1, 1 plus 2 is 3, so 3a. Divide both sides by 3, we get a equals -1. Okay, so now we have just a little bit of an issue because we need to solve for b and c. We can't plug anything in directly and end up canceling the a term because anything squared plus 2 is going to be positive. We can never get that to equal 0. So we need to do essentially kind of like what we did in the last one. So let's solve for, I'm just going to put b and c. And what we're going to end up doing, though, which is a little bit nicer, we're going to end up being able to substitute a -1 into a. So what we need to do is decide what can we let x equal. That'll allow us to solve for one of the other variables, b or c. Well, if we let x equal 0, then the bx term is going to cancel, and we're just going to be left with c. So we can end up solving for c explicitly. So let's let x equal 0. So that gives us 0 squared plus 3 times 0 minus 1 equals a, which is the -1 that we just found. So we can go ahead and plug that in. A times 0 squared plus 2 plus b times 0 plus c times 0 plus 1. And now we can solve this for c. We get -1 equals -2 from the a term plus the b cancels off, and then we're just left with c times 0 plus 1, so c times 1, so just c. So from all of that whole mess, we just get -1 equals -2 plus c. And solving this for c, adding 2 to both sides, we get c equals +1. So now all we have to do is solve for b. So I'm just going to erase solve for b and c since it ended up being solved for c. Now we need to solve for b, and this is actually pretty easy. Since we have a and c, we can go ahead and plug it in right into this equation up here again, and we can let any value equal x. So let's let x equal 1. So we're going to let x equal 1, and we're going to plug in for a and c, and we're going to end up getting 1 squared plus 3 times 1 minus 1. So once again, I chose 1 to plug in because it's an easy number. You could have plugged in another number. And then it's going to be equals a, which is -1, times 1 squared plus 2 plus b times 1 plus c, which is 1, times x plus 1, so 1 plus 1. Okay, so I'm going to assume that we can solve this. It's just a little linear equation. Just have to make sure your order of operations are good. We should end up getting b equals 2. So that wasn't actually too bad, just took a long time writing everything out. So now what we're going to do is go back up here and rewrite this, but we're going to plug in for a, b, and c, and that's going to be our answer. Okay, so this is what we end up getting for plugging in a, b, and c, and that's the partial fraction decomposition. Now let's do one more, and this one's going to be repeated quadratic factors. So far we've done just linear factors, we've done repeated linear factors, we've done a mix between linear and quadratic factors. Now we're going to do repeated quadratic factors with also a linear one in there. Okay, so first we recognize that the degree of the numerator is less than the degree of the denominator, so we don't need to divide. Also, we recognize that it's completely factored in the denominator, so we don't need to worry about factoring. So let's go ahead and set this up. So it's going to be 2x over x squared plus 1 squared times x minus 1. So we can see the linear factor. That's hopefully pretty obvious. It's the x minus 1. There's no exponent on it, so it's not repeated. The x squared plus 1 squared, that squared is telling us it's a repeated quadratic factor because x squared plus 1 is a quadratic. Okay, so let's go ahead and start with that quadratic factor. So it's going to be the same exact idea as when we had repeated linear factors. We need to have two different partial fractions. The first one is going to be degree 1. And the second one, we just keep on increasing the degree until we get to that exponent. Since the exponent's only squared, we just need to do it one more time. So it's x squared plus 1 squared. Okay, and then for the linear factor, there's only one linear factor, so it's just x minus 1. And let's see what we need to fill in on the top. Since the first two are quadratics, the numerators have to be linear, so it's going to be ax plus b for the first one, just like we did in the previous example. For the next one, it also has to be linear because it's still a quadratic. We have to use different letters though, so I'm going to use cx plus d. The linear one, we just need a constant, so it's just going to be e. So this one, what we're going to end up having to do is always solve for the linear one first if you can, which we will. We'll solve for e first. And then what we're going to have to do after that is we're going to have to equate the coefficients for each variable on both sides of the equation and use that to end up solving for a, b, c, and d. So we'll see that once we get there. For now, we have to multiply both sides by the denominator, x squared plus 1 squared times x minus 1. So we multiply every term by that, and let's see what cancels off. So on the left, we're just going to be left with 2x. On the right, we're going to have ax plus b. The x squared plus 1 is going to cancel, but we're still going to have one of them, and the x minus 1. Because it was originally squared over here. And now for the next one, plus cx plus d, so you parentheses around that. The x squared plus 1 squared will cancel, so we're just left with x minus 1. And then lastly for e, the x minus 1 cancels, so we're left with x squared plus 1 squared. Okay, so already you can probably tell that this one is messy. And for this one, like we just mentioned too, let's first solve for the linear constant, which is going to be e. So to do that, we have to choose the value that makes its denominator 0, which is x minus 1 equals 0, so x equals 1. So we're going to plug in x equals 1. That's going to end up canceling every other term on the right except for the term with the e in it. So we plug that in, we get 2 times 1 equals, and for the sake of simplicity, let's just recognize that if we plug in a 1 here and here, those huge terms are going to cancel. So I'm not even going to write them. We're going to be left with e times 1 squared plus 1 all squared. So just save some time there. And we end up getting, solving that for e, we get 4e on the right, 2 on the left, divide both sides by 4, we get e equals 1/2. So once again, just kind of doing that one in our head just because it's going to get crowded pretty quickly, and hopefully we can do that anyway. Okay, so that is 1 down, 4 constants to go. So now to solve for a, b, c, and d, what we actually have to do here is we need to completely distribute everything on this right-hand side. So I'm not going to go through and actually do that. That's just going to be super messy. So we would have to distribute this, multiply out x squared plus 1 squared, and let's plug in a 1/2 into e while we're at it. Okay, so let's say that we did that. So this is going to kind of be skipping a lot of work, but hopefully we're comfortable distributing, even though it might take us a long time because that's messy. So on the left-hand side of the equation, we just get 2x, so that's nice. On the right-hand side, if we end up distributing and combining like terms, for one of the terms, the little technique you have to use here, if you end up getting something like a x to the 4th plus 1/2 x to the 4th, we need to combine those like terms. Obviously, we can't combine a and 1/2 as a number, but what you do is you essentially you factor out a x to the 4th, and you end up getting a plus 1/2 times x to the 4th. So that's actually what we end up getting for the first term. And you have to use that little technique for pretty much all of these. So I'm just going to write it on out. So this is what we end up getting. So I know, yikes, it looks super messy, but you end up getting the 2x on the left, and you end up getting, here's your x to the 4th term, here's your x cubed, x squared, x, and then this whole thing is your constant. So the coefficient on the x to the 4th term, is a plus 1/2 x, or sorry, a plus 1/2. The coefficient on the x cubed is negative a plus b. Coefficient on the x squared is a minus b plus c plus 1. Coefficient on the x is negative a plus b plus d minus c. And then the constant is negative b minus d plus 1/2. So what we have to do is we have to equate those coefficients with the coefficients on the left. So it's easier than it looks because the only coefficient on the left is the x coefficient of 2. So when we are comparing these coefficients or equating these coefficients, we're going to be setting this equal to 0 because there's no x to the 4th term on the left, this equal to 0 because there's no x cubed term on the left, this equal to 0 because there's no x squared term on the left, this equal to 2, and then this equal to 0 because there's no constant term on the left. Okay, so let's go ahead and equate these coefficients. So we're going to do it for all of these terms. So for x to the 4th, like we said, there is no x to the 4th term on the left, so that coefficient is a 0. And then on the right, we have a plus 1/2. Okay, so obviously we can solve that for a, but let's just hold on a second. For x cubed, there's no x cubed on the left, so that's going to be a 0. On the right, we have negative a plus b. And hopefully you recognize that we can end up plugging in our value for a there and then solving for b. And that's how it's going to be for all of these. So for x squared, once again, there's no x squared on the left, so that's a coefficient of 0. On the right, the coefficient of x squared is a minus b plus c plus 1. And then for x, on the left, we do have a coefficient of 2. On the right, we have negative a plus b plus d minus c. And lastly, for the constant term, we have no constant on the left, so that's a 0. On the right, we have negative b minus d plus 1/2. And now we pretty much have 5 equations with 4 variables. So we actually won't even need that last one for the constant because we have 4 equations, 4 variables without it. So let's go ahead and solve these. From the first one, for a, subtract 1/2 on the left. We get a equals negative 1/2. For the next one, we're going to plug in a. That's 0 equals negative 1/2 plus b. Solve that for b. We end up getting negative 1/2 for b as well. And hopefully we can see where we are going with this. Next one, we're going to plug in a and we're going to plug in b. So it's going to be 0 equals negative 1/2 minus negative 1/2 plus c plus 1. A and b end up canceling each other there, and we're left with 0 equals c plus 1, c equals negative 1. And for this last one, it looks like we can just solve this directly for d. We don't even need the constant one. So we get 2 equals negative 1/2. So negative 1/2 plus negative 1/2 for b plus d, which is what we're looking for, and then minus negative 1 for c. And we solve this for d, and we're going to end up getting d equals positive 1. Okay, and then once again, we do not need the constant one in this case, but we wrote it down anyway. So we have our a, we have our b, c, and our d. And we already have our e from all the way up at the top. So all we have to do now is plug them all in right here, and that will be our answer. So let's plug them in. We end up getting that kind of a mess on the right. We can actually simplify that just a little bit. And we end up getting that mess. So all I did was simplify it by, instead of having the 1/2 in the numerator, I put that 2 down in the denominator. Okay, so decomposing the decomposition using partial fractions is a way of kind of breaking apart a rational expression and rewriting it as a sum. Okay, so that is it for this section.